Here he is.
Hello. I hope you're all feeling nice and refreshed after lunch, not falling asleep too much. I'm Graham Sutherland. You've probably seen me here before. This is my 7th talk in a row, and I've been here 8 years in a row. Previously, I was at Portcullis and Cisco. Recently moved over to Netitude Research and Innovation. I spend a lot of time at home tinkering with electronic stuff. I find it quite fun, so I thought I'd give a bit of a primer for folks who perhaps want to get into electronics and haven't had the chance yet, maybe wondering how to get started. And I tweet a lot, so if you're on Twitter, follow me, Sutherland. So why hardware? So obviously this is a security conference, and people like to mess about with IoT and things like that, but I think it's interesting to get into hardware, not just because of that, but because you can just build really interesting stuff. I like playing around with stage lighting, so I built some stuff to control stage lighting. Oh, sorry, I just called the wrong button. I built some stuff to control stage lighting. I like building things with lots of LEDs, so I've got some sticks with like 200 LEDs on them each, and you can control them by Wi-Fi. I think it's fun to play with hardware. Of course, on the work side of things, breaking hardware stuff is also something I do as part of my job. It's useful to be able to take some sort of board apart and understand what it does just by looking at it and Googling part numbers and things like that. So I'll be talking a little bit about doing that as well. So this talk outline, we're going to go over some basic physics. I'll keep it light. It's just the very basic things that you need to know to sort of understand how electricity works, really. And then we're going to go over some safety quickly, just because I don't want any of you coming away from here thinking, oh yeah, now I know how electricity works. I should go take apart this CRT monitor and start poking around inside it. No, don't do that. We're going to go over some common components that you'll see on boards, what they do, and what circuit diagrams look like, and what PCBs look like, and how you can interpret them and that kind of thing. Some stuff about logic, so digital logic, and how that works in electronics, processors and different types of them, interfaces that those processors use to talk to other things, some tools that you might want to take a look at and maybe get hold of, some options that you've got there, and at the end I will put up a slide with a big resource dump that you can then, rather than me reading them out, you can just take a photo with your phone or something and then go and dig through that on your own time. So let's start off with some physics, because of course that's what you want to do at 3 o'clock in the afternoon, right after lunch. So we can start with some definitions. Voltage, measure it in volts. We give different symbols, different letters to describe these different sort of parameters. For some reason we use I for current, because resistance, we measure that in ohms, and power, measure that in watts. Now, you've all heard of voltage. Voltages don't exist in the absolute. A voltage is a sort of energy difference. So when we talk about voltage, we're talking about a voltage between 2 points. So for example, if you've got a 9-volt battery, there's no sort of magic 9 volts that exists. What it is a voltage between those two terminals on the battery. This is quite a sort of famous diagram of how voltage and current and resistance sort of all fit together. So voltage is kind of like the force that pushes things along, pushes the currents along. The more voltage you've got, the more current that is likely to flow because of that. Resistance tries to stop that. So current is sort of driven by how much voltage you've got in the first place, and the more resistance you've got, the less current flows. So they sort of the voltage and resistance are kind of at odds with each other. So we describe that in maths using this thing called Ohm's law. So if you look at this, you see that sort of the voltage is pushing and the resistance in ohms, measured in ohms, is resisting. So I, current, the amount of current that flows through a circuit, is equal to the voltage of that circuit divided by the resistance of that circuit. And then you can use some basic algebra to rearrange that. So if you know any of the other two, you can work it out. So for example, if you know that you've got a device that is being supplied with a particular voltage, and you know how much current is flowing through that, you can work out what that the resistance of that device is. And same with, if you know how much current is flowing and you know what the resistance is, you can work out what the voltage is. I'm going to quickly go over power, but we're not going to talk about it too much in this talk. Power is the product of voltage and current. Power is literally the amount of energy consumed by a thing in 1 second. So 1 watt is 1 joule per second. So if you've got a 60 watt light bulb, that's turning 60 watts of electrical energy into 60 joules of electrical energy into light and heat every second. These are just other ways to state it. Again, it's just algebra. At the bottom, you might notice one is slightly different because we can plug Ohm's law into this. It turns out that if you've got a device that you know the resistance of and you know how much current's flowing through it, you can work out the power without needing to know the voltage. It's quite useful. But we're not really going to touch on this too much. It's just useful to know. Now, safety. How many of you have heard the phrase, it's not the volts that kill you, it's the amps? I hate this advice. I get told by electronics people that it's correct, but I know it's correct, but it's terrible, terrible advice because without context, most of the time this advice is given is to people who don't really understand electricity all that much. And this on its own is really misleading because which of these two power supplies is more likely to kill you? The one with lots of amps or the one with lots of volts? The answer is the one with lots of volts. So electric shocks, human body resistance in the worst case, if you've got like a cut and you've got wet hands and it's on a bad day, it's down and around the 500 ohms range, 500 to 1,000 ohms. The lethal current, that is how much current needs to flow through your body in order to cause fibrillation, basically to stop your heart, is about 100 to 200 milliamps. So that's 0.1 to 0.2 of an amp. Using Ohm's law, you can work out that effectively about 50 volts is enough to kill you in the worst case. But you're probably thinking, hang on a minute, I've shot myself on the mains before. It hurts like hell and get a bit of a dead on. It didn't kill me. It's way higher than 50 volts. Well, that's because generally dry human body resistance is much higher. So if you've got dry hands and you catch yourself on the mains, you're more likely to be up at around 10,000 to 100,000 ohms. And again, if you put those numbers in, you get more like 23 milliamps, which is much lower and less likely to kill you. You can still obviously do yourself some damage with it, but yeah. So these are sort of the approximate shock thresholds. You notice there's a difference between AC and DC. The reason for this is that your nerves work on electrical impulses. Now, DC is just a constant current that flows. AC is kind of like turning it on and off very, 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 very quickly. And your nerves respond to changes in voltage. So because of the AC is like turning it on and off very, very, very quickly, it makes it much harder for your muscles to sort of compensate for that voltage flow. So AC can cause your chest muscles to compress so much that you can't breathe and you'll suffocate. So basically, don't faff about with main stuff while it's on, because it's a terrible idea. Is Infodocs in here? Maybe not. But he suggested some alternative names for some of these, which I thought were quite amusing. Yeah. Try to avoid silence. So it's the voltage that usually decides your fate. So it is the amps that kill you because it's how many amps flow through your body that determines whether you live or die. But what determines how much current flows through you is how much voltage you've got in the first place. So it's important to know that. In fact, one last thing here. 3 things that you should never take apart. Microwaves. They've got a big transformer in them. They step the voltage up to several thousand volts. You touch that, you're probably dead. CRT, anything with a CRT monitor. I know some of you are quite young and probably have never even seen a CRT monitor. But yeah, don't take those apart. That's a terrible idea because they've got you can go all the way up to about 14,000 volts on the electron gun on that. They will kill you. And the third one is anything to do with driving neon lights. The 6 kilowatt power supply I showed a minute ago, that's a neon light driver. Don't take those apart. Other than that, you're mostly okay. But try to stick to non-main stuff that sits around 5 to 12, maybe 19-ish volts. You're mostly safe. So we're going to talk about components. So the things that make up an electronic circuit. There's two main categories of component, passives and actives. If you ask me to describe the difference between passive and actives, I'd say there's two ways of looking at it. One of them is the physical definition. I can see you're laughing at me there. The physical definition is a massive pain in the arse to understand and not very intuitive. Effectively, one of the main things is that active components can amplify power and passive ones can't, but then there's some grey area around that. It's a little bit weird. Don't worry about it too much. We'll talk about it a little bit more in a minute. Passives here, you can see on the left here, these are all surface mount. You might be more familiar with components that have actually got leads coming off them, but in most things that you take apart these days, they're all going to be surface mount components rather than through hole. So these are resistors. They're usually black, sometimes blue if they're like special precision resistors, but they're usually black. Usually got some numbers on top. These are capacitors, they're usually brown. And these are also capacitors, they're a different type, but you've got these little cans. Sometimes in things like power supplies, you'll see much bigger capacitors. So resistors. We mentioned resistance already, we mentioned Ohm's law. Resistors effectively limit the flow of current. And a good description, so this little zigzaggy thing, that's the symbol for a resistor in a circuit diagram. There's also an American style symbol, which is actually just a box, because, it's easier for them to understand. No, it's not. Sorry, Fitz. So an example of where you might see a resistor used is, let's say you want to power an LED off a 9-volt battery. You stick an LED directly over a 9-volt battery, and it's going to go very, very bright, then it's going to go very, very dim, and then it's going to go very, very smoky. Because what's happening there is, because the voltage is so high, the LED pulls a lot of current, too much current, and therefore too much power, which gets dissipated as heat, and then it catches fire. So what you generally do is you put a current limiting resistor in series with that to ensure that the LED can run at that higher voltage, because an LED only usually likes about 2.5 to 3.5 volts, depending on the LED. Capacitors. Think of them like really, really tiny rechargeable batteries. They can't store much energy, but you can charge them and empty them fairly quickly. And you can do that many, 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 many times, unlike a battery where, rechargeable batteries, you recharge them 10, 20, 30 times, at least with the old school batteries, and they stop working. But they take a very long time to charge, like LiPo batteries and things like that. You often see them in power stuff. They're used in a lot of things. They're filters, radio frequency stuff, blah, 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 blah. But mostly what we really care about when we're sort of taking things apart, they're mostly used for power stuff that we tend to be looking at. So they're measured in, the capacitance is measured in farads. You will very rarely see a capacitor that has a capacitance of more than a farad, or even anywhere near a farad, because a farad is quite a lot. We're talking very big capacitors for that. Generally, you're looking more around the sort of like microfarads range, maybe a couple of millifarads. So ceramic capacitors, or otherwise known as MLCCs, multi-layer ceramic capacitors. These are smaller devices. They've got very small capacitance, anywhere from, the bigger ones are in like the single digit microfarads. They go all the way down to like picofarads, very, very, very small amounts of capacitance. They're non-polar. You can connect them in either direction. There's no requirement to have a positive voltage across it in one particular direction or the other. The other type is electrolytic. So if you remember on the slide before, we've got the two types of capacitors. The MLCCs were the ones on the left. The ones that look like cans on the right, those are electrolytic capacitors. These are polar, which means that if you connect them over a voltage source in the wrong direction, they will blow up or just not work. They store more capacitance. They've got more capacitance. That you can generally get up to hundreds of microfarads or even a few millifarads in most of them. You can go even bigger than that, but you generally don't see them in most types of devices. Now you might be thinking, well, why even bother with the little ones if you can have the big ones? Well, they're not perfectly conductive. They actually have an internal resistance. They have this thing called ESR, which is called equivalent series resistance. What that means is they can only charge up and discharge at a certain speed because there's a limit on how much current can flow because they have a resistance. So these ceramic capacitors, the little capacitors, have a much lower ESR, which means that they're very good for high frequency stuff. So say, for example, you want some sort of energy reservoir, some power. You're powering some device and you want to make sure that it's got very smooth power. The problem with big capacitors is they can't provide power very quickly. They can't change the amount of current that they output very quickly. So ceramic capacitors are really good for that because they've got a very low internal resistance. Whereas electrolytic capacitors, they can store a lot more energy, but they've got a higher ESR. So there are a couple of other types at the bottom, tantalums, aluminium polymer, and film. They basically sit somewhere across the spectrum between them. Some of them have additional properties like being able to withstand very high voltages and things like that, but that's not too important. Well, it is if you're building a circuit that requires that sort of thing. There's another type of passive called inductors. They're effectively like a little wire coil. I'm not going to go into them that much I'm not going to go into them at all because you mostly don't need to know about them. Other than if you see one, it's probably related to power or radio stuff, but mostly power. Actives. So you've got these active components as well as passive components. So active components are things like transistors, things like pole operational amplifiers, op amps, and things like logic gates. So these are devices that sort of can switch things on and off. They usually have a power supply, pins on them that take some sort of power supply. So for example, you've probably heard of if you've ever looked into, any electronic stuff, you've probably seen an example of a transistor switching an LED on and off. So that's those kinds of sort of classes of devices. Won't go into them too much. We'll talk about logic gates later. Diodes. So diodes are a weird one. There's an argument, in the strict definition, they are active components. But most electronics engineers just treat them as passives. So diodes allow the flow of current in one direction. If you try and pass current in the wrong direction, they don't pass current, with some slight exceptions. So they're quite useful for things like protecting against reverse polarity of attaching a power source backwards. So if you've ever seen a device where you can connect an 9-volt battery, and if you connect the battery backwards, it just doesn't do anything. Chances are there's a diode in there protecting it from protecting the circuit from inverse polarity. Because if you don't have one, you might blow a bunch of stuff up. LEDs are also diodes, light emitting diodes. But yeah, it's one of these ones where they're sort of they sit on that kind of border of being active and passive. It's a little bit weird. So circuit boards. I'm guessing a lot of you, if you look at a circuit board, you're going to see something like this and go, "Oh my god, what the hell does any of that do?" It probably looks like a giant mess. There are some indications. So, for example, you can Google some of these part numbers. I'm guessing by the fact that says Samsung and it's got some big number in there, that's probably RAM or flash or something like that. But it can be quite difficult to sort of dig around and work out what this all does. So let's just take a more ridiculous example. Anybody know what this is? Take a good guess. Oh, and it is a graphics card. This is an NVIDIA 1080 with the heatsink taken off it. Anybody who's built a PC before can probably guess what some of this stuff does. But so Power on the right, these power connectors, you've got these 6-pin and 8-pin power connectors. GPUs use a lot of power, too much to run through this little PCIe connector at the bottom. So they have these big power connectors. These are what's called SLI connectors, so that you can connect multiple graphics cards together and improve performance and stuff. Then you've got your outputs here, so you've got your HDMI and your DisplayPort or whatever. Now, a lot of working out what part of a circuit board does what is actually just sort of the geometry of the thing, the topology, the way it's all laid out. So we know that there's power coming in here. We can probably guess that this is the GPU itself, the processor. So we can see some power stuff coming in here. We can see a bunch of electrolytic capacitors, these big CAN capacitors. A bunch of stuff over here that looks like a bunch of capacitors and some other thing here. These are actually inductors, but it looks like some power-related stuff over here and some chips here that might be related to power, maybe. Then you've got the GPU. We know that a GPU has a bunch of VRAM on it. Well, these are RAM chips that sit around it. And then you've got a bunch of stuff here that's possibly related to maybe output, maybe some other auxiliary functions. And you've got this input here, so there's maybe some stuff going on around this connector is related to the electronics here. So if I wanted to know, for example, so GPUs have firmware. If I wanted to guess where that firmware was stored, we've got power here. This stuff also looks related to power. So probably all this stuff over here is just power. None of this looks like it stores firmware. What it looks like is it's just all RAM, chip, which means that it's probably got to be somewhere in this bit here. Now, firmware is usually stored on little flash chips. I happen to know that this graphics card has a dual BIOS functionality, like one stock BIOS and one overclocked BIOS. So there's probably going to be two chips for that, and I can see one little 8-pin chip here and one little 8-pin chip here, which means that they're probably the BIOS chips. So just based on taking a look at the board and how it's laid out and where things go in, where things go out, where power comes from, where the connectors are, if the board is well designed, you can sort of infer a lot just from that. That's not the only thing that you can use. So when people are designing circuits, let's say you've got 3 engineers working on a circuit, or even 50 engineers working on a particular design. They need to be able to talk to each other about particular sections of the design, or this thing around here. Well, rather than just saying that transistor over there or that diode over there, what they do is they give each part an identifier, a unique identifier for the design. So these usually start with a letter or a sequence of letters describing what the part is. So if it's a resistor, it starts with R. If it's a capacitor, it starts with the C. And then you've got a number after it, which indicates which one it is. So C1, C2, C3, C4. For some reason, well, actually, you might be wondering why transistors are Q, if you can actually read that. It's a bit of a weird one. Well, T was already taken for transformer. And I'm told the reason that it's a Q is that old transistors used to be in like a round case, and it had a little metal tab coming off it. And if you look at it from the bottom, round circle with a little tab coming off, looks like a Q. Bit of silly knowledge. So on that particular board, if I just go back a couple of slides. So this is a zoomed in section of this area here. And you can see that we've got some reference designators on here. So you've got the C104, C107. So all of this is capacitors. So these are capacitors. These are L32, L25, whatever. L means inductor. So we know these are inductors. Inductors, big inductors, mostly about power stuff. Q, that's transistors. So if we go back, we can guess that these are all capacitors here. These are all inductors. And these are all transistors. These are all power, what's called power phases for that particular design. So we know that that's all related to power. But of course, you don't just, when you're designing a board, you don't just start on the PCB. You want a circuit diagram to sort of describe the circuit initially, and then once you've got that layout, you can turn that into a PCB design. So I'm guessing sometimes you look at you might find a circuit diagram online and think, what the hell does any of this do? This is from XKCD. Of course, there is always a relevant XKCD. I'm guessing sometimes you take a look at it and you go, oh my god, what does any of that do? So here is another thing that is not particularly simple. I mean, it is quite a simple circuit, but it's not completely trivial. Just to give you an idea of what circuit diagrams look like and how to interpret them. So you can see here that they've used the American-style resistor symbol. So R1, you know that's a resistor. D1, you know that's a diode. C3, you know that's a capacitor. And you can see that with this plus sign here, that it's an electrolytic type because it's polar. Here, no plus sign, flat lines, non-polar, so it's like a ceramic capacitor. Usually, on designs, you'll see dots where these lines join to say that these are connected. Say, for example, here, no dot, not connected. Just to be confusing, no dot, still connected. People are bad at making circuit diagrams. So this is actually a voltage doubler circuit, not important. So this is just saying go to power. This is just saying go to ground. This is a slightly older circuit diagram. Different circuit, same chip, 555 timer. Again, different symbol for the electrolytic capacitor, but it's still got this positive symbol on it, showing that it's electrolytic type. PV1, push button. It's got this little drawing of a push button here. LEDs, resistors, and you can see that this has got a reference designator of R3 and the value of 470 ohms, which is sometimes just written as an R. This is a really old style design. You can tell because they use this symbol for ground, which is a really old symbol for ground. Do you see that ever anymore? Yeah, no, it's really rare. TVs and like VCR. Yeah, like old TVs and VCR. Yeah. And then, without actually even having any symbol showing where the power's coming from, you've just got this thing that just says what this entire rail at the top runs at, so what you connect it to is 5 to 15 volts positive. And one thing I will point out from the previous one is sometimes instead of a value, you'll see a part number. So you've got diode 1, which is a 1N4007 diode. So that's the kind of thing you expect to see on circuit diagrams. I'm going to talk a bit about logic. So logic, if you saw Fitz's talk, he mentioned some stuff around that briefly. So logic, you know what binary is? Ones and zeros. In circuits, it's represented with high and low voltages. So a voltage of 0 volts or a low voltage is a 0, and a voltage of a positive voltage usually means a 1, usually. So generally, yeah, zeros, 0 volts, ones, positive volts. Logic levels. So when we talk about positive voltage, how much positive voltage? Is it 100 volts, 5 volts, whatever? Usually you'll see these, 5 volts, 3.3 volts, 1.8 volts. It depends on the device. An important thing to note is if you try to connect a 5 volt logic device and a 3.3 volt logic device together, bad things can happen. You can fry it. So this is an oscilloscope trace of a device that's outputting a 0, then a 1, then a 0, then a 1, and then a 0. And you can see that it's about 5 volts. So you've got a 0 volt, about 5 volts, 0 volt, 5 volts. So that's 0, 1, 0, 1, 0. Same thing again, but with 3.3 volts. So again, the 1 is about 3.3 volts and the 0 is about 0 volts. So don't blow up your hardware. You might be familiar with a few of these devices. They have different voltage logic levels. So some of them run at 5 volts, some of them run at 3.3 volts. Some of them, like the Teensy, they run at 3.3 volts, but the inputs will take 5 volts. They're tolerant. It's what's called tolerant. But if you put 5 volts into, say, a Raspberry Pi, GPIO pin, input pin, you can blow it up. So don't do that. I'm guessing you're all roughly familiar with digital logic stuff in terms of you've heard what an XOR and an AND is, the same sort of thing in programming. All of this comes from hardware. So all of these bitwise operations just come straight from hardware. So you've got two inputs, A and B, in these particular devices, or one input in the case of the NOT gate. And they perform some sort of function, and then they output something. We usually use Q as the output. I cannot remember why. Reasons. Possibly related to the fact that Q was used as a transistor, and these are made out of transistors, but I don't know. Any idea? Yeah, no idea. So say, for example, you put a low voltage, so 0 volts here, and a high voltage, say 5 volts here. You get a 0 out here because it's an AND chip. It requires a high voltage here and a high voltage here to output a high voltage here. And you can stick a lot of these gates together and other types of devices to make various types of logic circuits and build processors and blah, 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 blah. Now, one thing to mention is our clocks. So I'm guessing you've all heard, you all know about processor clock frequencies, things like that. So, you get a Intel Core i7 at 3.5 gigahertz or whatever. Well, what that really means is devices that have digital devices that have a kind of state. So whether that be memory or whether there'll be some sort of control device in there that's doing some sort of digital processing. Could be a microcontroller or a microprocessor. What happens is that these devices only perform operations when the clock ticks. So usually what we say is it's on the rising edge. I apologize for the lack of contrast in this image, but I will just sort of draw the red line just in case you can't see it very well. So what's happening here is a clock signal is just something that goes 0, 1, 0, 1, 0, 1, 0, 1 very, 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 very quickly. Or very slowly, but usually quickly. And what happens is these devices perform an operation on the rising, usually on the rising, but sometimes on the falling, but usually on the rising edge of this clock. So as the transition goes from 0 to 1, we call that a tick, and then 0 to 1, another tick. Some devices do it on the falling edge, but that's not important really here. So on the falling edge, it would be from 1 to 0, but most things on the rising edge. And the time difference between each tick is called the clock period. And if you take 1 over the clock period, so say that clock period is, a millisecond, let's just say. So the time between here and here is 1 millisecond. You 1 divide that, you get 1,000. That's 1,000 hertz or 1 kilohertz. So that's where you get clock frequencies and things like that from. So we're going to talk about processors. Processors are sort of split into 3 main types. You've got microprocessors, microcontrollers, and programmable logic. Now, programmable logic isn't necessarily a processor, but I've put it under this category because it's easier to talk about here. So microprocessors they fetch instructions, they decode those instructions, and then they execute them. So if you've ever done anything to do with processor design or processor internals, if you've ever done anything in a course module, you might have heard about the fetch execute cycle, which is fetch an instruction, execute the instruction, fetch the next instruction, execute the next instruction. Microprocessors use external memory, so they have no RAM on board, not in the chip. So they have to put that separately. They have no flash on board, so they don't store any code on board. This is less true of things like desktop processors because they really muddied the waters with that sort of stuff. But we're talking, old school original processors, microprocessors. Everything was kept external. They use external peripherals as well. So, for example, if you wanted to store some configuration variables across reboots, you can't do that inside a processor because there's no sort of like permanent flash inside there. An example is the Zilog Z80. I'm looking at this room. I'm guessing many of you will have never heard of this thing. It's the processor that powers the ZX Spectrum. I chose this one specifically because if I have said an Intel Core i7, most of the things I wrote on here about them using external memory and peripherals would be wrong because they just really, on a modern system, it's very, very bloated and there's lots of things in there. But yes, Z80, all it really does is these first three things: fetch, decode, execute. Microcontrollers, however, they contain a microprocessor, but they also contain memory, so they have their own RAM built in on the chip. And they have program flash built in. So the idea of these is you can program a single chip with some code, and that chip on its own, as like a standalone device, will execute that code. It has its own RAM inside it, and you don't need the supporting components externally. It also usually has things like internal peripherals. So, for example, some of them have like a Wi-Fi interface built into them, things like that. They're sort of a general purpose device. So an example is the Atmega 328P, which again, you've probably never heard of, but I'm guessing you have heard of an Arduino. That's the chip that's inside of an Arduino Uno. So that's what powers that. Now, programmable logic is a bit of a weird one. So if you remember the logic gates I showed earlier, think of it as like a giant configurable array of logic gates. You can sort of say, okay, I want this logic gate, and then I want to connect it to this logic gate, and et cetera, and then that's a block, and then I want this block to talk to this block. It's kind of like logic Lego inside of a chip. So yeah, it's an interconnected logic. It doesn't execute instructions, not on its own at least. It doesn't execute instructions. It has a sort of mesh of logic stuff glued together. They're used for more specialist applications. In some cases, they're used for just like, okay, we want this whole bunch of like interconnecting logic to talk to handle some specific thing, but we don't want to have, say, 70 chips to implement this one thing. So they'll just get this a PAL or a PLA, which is a programmable logic array, just to go and do that kind of thing. You can make them implement microprocessors and microcontrollers because at the end of the day, processors are just a big array of gates. Memory is just what's called a flip-flop ICs. Each flip-flop can store one bit of data. And if you stick a big array of them together, well, now you've got 8 bits of data, so that's a byte. And if you stick a whole load of them together, you can make kilobytes of it, etc., etc. So you can implement microprocessors or microcontrollers on these types of devices, particularly FPGAs. An example of an FPGA is the Lattice ICE40 FPGA. The reason I mentioned this one is because it's fairly hobbyist accessible. The chips are fairly cheap. You can buy a little USB dev board called the Tiny FPGA. It's a pretty fantastic thing. I think it's like $60 or something, is it? Is it even less? Wow, what, $35, yeah. So if you want to play around with FPGAs, you can do that there. And an example application is, I don't know how many of you have heard of RISC-V, but RISC-V is kind of like an open source processing architecture. So, you've got like x86, you've got ARM. Well, RISC-V is a different architecture and it's designed to be open, so it's an open specification. And there are a bunch of implementations, RISC-V implementations for FPGAs. So if you wanted to build a device that's open source all the way down to the sort of processor logic level, you can use that to build, use FPGAs to do that kind of thing. Interfaces. Now, these devices on their own, not very useful unless they can talk to other things. So just like with a laptop, you might have an Ethernet cable, you might have USB. Microprocessors and microcontrollers need interfaces to talk to other peripheral devices. Say, for example, flash chips, temperature sensors, external memory, gyroscopes, that kind of thing. Even just LEDs. So the most simple is GPIO. If you were in Fitz's talk earlier, he mentioned GPIO. So GPIO is general purpose input-output. They're effectively just pins that come off of the processor and that you can reconfigure them to do different things. So the most simple thing you can reconfigure them to do is be an output or an input. So an output, so this is Arduino code here. An output, you can configure a pin to be an output. You can write a high to it, which sets the voltage high, and you can write a low to it, which sets the voltage low. In fact, this example blinks an LED on and off with a 1 second gap in between. Obviously, you can do the same with inputs and just read whether it's a high or low voltage as well. UART. So UART is often misdescribed as serial. Serial just generally means that it's something that happens in one big line. It's not parallel. But a lot of people call it serial. Effectively, all it is a way of sending bits down a wire in a sequence. So you get this start bit, and then it will transmit bits 1, 2, 3, 4, 5, 6, 7, 8. So 0, 7, so that's 1 byte, and you get this stop bit. So you can send bytes down the wire. So what this code does is it says, okay, I want to send 9600 bytes down the wire every second. So it's called 9600 baud. The older ones of you will know what baud is more than the younger ones because you'll have been playing with old school modems. So all this is really doing is saying, okay, send the ASCII value for H down the wire, then E down the wire, etc., etc., etc. So you send hello world. So you can use it to send text, arbitrary bytes. It can also receive as well. So you see UART are used for like debug outputs on like router boards and things like that all the time. Now RS-232 is also described as serial. They are not the same thing. RS-232 is quite it's an old protocol. If anybody remembers serial connectors on the back of old PCs, the old 9-pin serial connectors, DB9s. So the way that works is you've got a voltage all the way up as high as 15 volts and all the way down as negative 15 volts. And what happens is, in order to represent ones and zeros, anything between +3 and +15 is actually a 0, and anything between -3 and -15 is actually a 1, just to be weird. So here you've got it's the same sort of scheme as UART. So you can see here you've got this start bit and stop bit, and the bits transferred in between. This is literally the same thing. You've got this start bit, and you've got 1, 1, 0, because you've got these represents a 1, this represents a 0, all the way through, and then you've got your stop bit. It's important to know the difference between these two things, because if you try to plug an RS-232 output into a UART receiver, you will probably blow up your UART receiver, because plus and minus 15 volts is not meant to go into your UART receiver. UART operates at the logic level of the board, so as we were discussing before, 5 volts, 3.3 volts, 1.8 volts, sometimes lower, but you're usually going to see 5 volts and 3.3. So yeah, don't put that into the wrong thing. But you can get RS-232 receivers, USB RS-232 receivers dead cheaply online. Again, you can buy like 50 of them on eBay for nothing, which is good because about 10% of them will be broken when they arrive. SPI. So SPI is a little bit more complicated than the previous two. SPI stands for Serial Peripheral Interface. Again, flash chips, if you remember the BIOS chips that I was mentioning on that NVIDIA card, they get spoken to via SPI. Generally, you have this concept of a SPI master and SPI slave. Slightly problematic terminology, but this all comes from like the 1970s or something, so attitudes were slightly different. These days, you might also see primary and secondary. The idea is, if you remember, I mentioned the clock before. So, master device provides this clock to say when data should be read off the or sent. So this is MOSI, master out, slave in, master out, slave in. So it's going out of the master, into the slave, and then here master in, slave out, master in, slave out. So the idea is this is essentially like transmit and receive. Then at the bottom you've got this thing called SS. This can also be called DS or CS. So SS means slave select, DS means device select, CS means chip select. They all mean the same thing. And what that basically means is when the SPI master asserts the SS signal, the slave starts listening. And the idea is that to save pins, because adding more pins to devices is expensive, to save pins, you can have, let's say you've got 5 slave devices and 1 master device. You can have the clock and I/O lines shared across all of those, and then 1 select line per device. So the idea is that then, if you want to talk to one specific device, you just assert that 1 pin for that chip's select, and then send stuff over the rest of the wires. Again, you can just use this gets used all over the place for small devices like temperature sensors and flash memory and things like that. I2C is another thing that's very similar to SPI. It's used in pretty much exactly the same types of application. Again, it's shared bus sort of design. Except in this particular case, I2C only has 1 data line. It's bidirectional, so the devices transmit and receive across across that 1 line, and the SCL at the bottom is the clock again, which is provided by the master and consumed by these. Don't worry too much about this. All this means is that there's a couple of pull-up resistors on here. So the idea is that when these devices stop talking, it causes the voltage on these lines to sort of float weakly up towards the voltage rail. That's just to do with how the protocol works in terms of the literal hardware. But the way that these devices can tell which one the master wants to talk to at once is they each have an address. The address is usually, I think it's an 8-bit value, is it? It's 7. So, of course, it's a 7-bit value, just to be confusing. 7-bit value. Usually, you get the option. So, in the parts datasheet, you'll see how you configure that. Usually, there's like a couple of pins that you pull high or low to configure what that address is. You usually have fairly restrictive configurability. Like, you can't configure the full 7-bit address. You'll be able to configure, say, 3 bits of that address. So the idea being, if you've got 3 of the same device, you can, multiple of the same device, you can just configure those to be slightly different from each other. I haven't quite got time to go into SMBus, but SMBus is a kind of more modern version of this that runs on top of I2C, and it's used in PC motherboards a lot. JTAG. So again, if you were in Fitz's talk earlier, JTAG will have been mentioned. So JTAG, Joint Test Action Group, which is a weird thing to call an interface. Really, it started out as kind of a way to test that boards had been properly, that were working properly, that from a particular connector, you could see that all of the parts that were on there were all talking, but were all available and working, and you could talk to them. Then they started adding in debug functionality. So JTAG's really cool because you can, if you get it configured right, which is a massive pain in the arse most of the time, you can start debugging the chip. So you can cause the chip to reset. You can start going through with like GDB and stepping through the code that's running on that processor. And you can dump memory and things like that. And then ISP and ICSP. ISP is in-system programmer, and ICSP is in-circuit serial programmer. They're effectively the same. I think there's like slight differences in the actual protocol and how they work, but they effectively do the same thing. So what used to happen way before this existed was if you had a device that had to have some firmware programmed onto it, and the boards were going through the production line, you had to pre-flash those chips separately before they got soldered onto the board. That's a real pain in terms of like mass manufacturing. So what they did is they came up with this thing called ISP or ICSP, and the idea is you've got like a header that's on there that you can then, while that chip is in the circuit, use it to program that chip, program the firmware once there. It also means that you can use it to reflash existing boards once you've got them. So there are cases where you can flash like third-party firmware on something with ISP and ICSP. So some tools. I recommend you get a multimeter. Don't get like the absolute cheapest Chinese knockoff one, because chances are it'll say it's safe for 230 volts or something, and you'll stick it in and then it'll explode. Just get any old branded one. Get a cheap one. Doesn't really matter. You don't need massive precision out of it. It's just useful for telling where a power rail is, for example. So does this pin have 5 volts going to it? Yes, this pin does have 5 volts going to it. So multimeter, dead simple. They're dead easy to use. You can Google if you're confused about how to use one, but you can find out online. You can use measure current as well and things like that. Oscilloscopes. Oscilloscopes are really useful because you can use them to debug circuits, but you can also use them to reverse engineer things. The DS212 is kind of cheap. I think it's like £60 or something, 50, £60. Looks like a smartphone. And it's got a couple of channels, and you can hook that up to things and see the signals that are flying across a particular pin in real time. Dead useful, dead cheap. I recommend getting one if you're just looking for like a cheap option. You've got this other thing called this Open Workbench Logic Sniffer. What this is, it's a bit like a bus pirate, but with lots and lots of pins on the end, and it can only receive. And the idea is each of those pins can only receive a logical 1 or a logical 0. They can't report any more granularity than that. So it's a logic analyzer, but there's some software that comes along with that that allows you to define what each pin means for a particular protocol, and then decode the results of that. So if you've got, say, for example, SPI bus, and you want to be able to sniff the data that's coming off that, you can hook it up to that bus, and it will tell you all the data that was going across and show you where the transactions start and stop. Picoscope is a more expensive option. It's a USB oscilloscope. This is more of a professional tool. I have one of these. It's really great. The software that comes with it, I think, runs on Windows, Linux, and Mac. It's pretty decent. They are quite expensive. I think the cheaper models start at around £600. I recommend going on eBay and looking to see if you can find second-hand ones and B-stock models, because when new board revisions come out, Picotech dump all of their old stock models on eBay for I think it's like 50% of the retail price. They're great bits of kit. Alternatively, if you want a proper oscilloscope and you don't want to pay too much, but you don't care if it's massive, bulky, heavy, and power hungry, get yourself an old CRT scope. I have one of these. It's older than me, and it still works. It's pretty fantastic. That's good. Another good option. In terms of interfaces, FT232H boards are absolutely fantastic. You can get them very, very cheaply. Again, about seven quid. Like from Fitz's 7 hacks for £7, was it? I forgot the name. Sorry. You can do quite a lot of things with just this board. It speaks SPI, it speaks I2C, it speaks UART. It's very useful. There's the Bus Pirate. I don't like it that much. I like the Hydra Bus. The Hydra Bus is like the Bus Pirate, but faster, better, and has a bunch of extra support. Glasgow is not finished really. It's an ongoing project. It's being built by two people on Twitter, Whitecock and Markan42. It's an FPGA based tool. The idea is that instead of having one chip that tries to do a lot of things, you have a reprogrammable chip that you say, okay, I would like the specialist application, and then you flash that particular application on it for doing one specific thing. So say, for example, you want to talk HDMI, for example, like other tools, that would be very difficult to do. With Glasgow, you just flash a HDMI core onto that and then run it. The idea, I think, is that they're going to cost about £70, £80 when they come out. There is only about 10 Revision C boards in existence, but if you ask nicely, there are some people on Twitter who will make you one. So keep an eye out for that, because it's a pretty cool tool. For development stuff, for building your own things, I recommend Arduino. It's a fantastic platform to get started on. It's really easy. The documentation is written with people who have never done electronic stuff in mind. Kids use it. You can work your head around it very easily. It's quite nice. Node MCU boards are like Arduino boards, except they run Wi-Fi. They run on what's called an ESP8266. And yeah, you can use them for doing like Wi-Fi IoT stuff. I have an absolute ton of them. The LED sticks that I mentioned, they're run off Node MCU boards so that you can control them over the Wi-Fi. You can also use Raspberry Pis and SBCs, single board computers. I don't really like them that much for doing hardware stuff, but some people do. Parallax Prop just gets a mention here. It's a little bit like an Arduino. It's not quite so well supported, but it's pretty cool because it's got like multiple cores. So the idea is that you get like 8 or 16 cores in one chip. They're a little bit more expensive, but if you want to do stuff that's got like multi-core support, so if you want to do something that's very, very parallel heavy, you can play around with that. For radio stuff, I'm just going to quickly go over this. You can get an RTL SDR for about £10. It's a TV tuner device that you can repurpose as a software-defined radio. Then you've got the sort of mid-price commercial options, which is Hack RF and Blade RF. And then if you want to go pricey, USRP, the pricier ones can transmit as well as receive. So in conclusion, I think more people should play with hardware. I think it's one of these things where you don't need to necessarily have a huge amount of like domain background knowledge in electronics to start playing. Kits like Arduino make it super easy. And you can take the things that you learn from building things and use it to apply into your work for breaking things. So yeah, I think you should play around with that. And that is the end of the talk. And as promised, here is my giant list of things that you should go and take a look at. Feel free to take a photo so you can dig it out later.